Hello, everyone. Welcome to this session about securing the supply chain for your Java applications. Let's start right away by defining what is a software supply chain. Well, we build software to solve a problem, typically. We identify this problem, we realize, hey, we can use software to solve it and deliver value to our end users, to our customers, to our business. So we implement it, we go through different stages, and eventually we're gonna deploy that application, that's a piece of software in production. And that's where it delivers value. Now, everything that goes from the original implementation of the idea up until we are in production, where our software finally delivers its original value, that's what we call a software supply chain. And it includes everything. It's the set of everything needed to deliver software to production. That includes code, includes dependencies, tools, practices, and people. And I'd like to highlight the last two items there, practices and peoples. It's not just about tools. We need the right practices, and we need people adopting those practices and have the right mindset of working with software. The next question is, why do we care about the software supply chain, and why do we want to secure it? So I have a question for you now. Have you heard of the Log4j vulnerability from a couple of years ago? Well, almost everyone, right? So that's enough to claim that supply chain security is important, because that vulnerability impacted millions of applications all around the world. And I bet that after 2 years, there are still applications out there in production which have not been patched. So supply chain security is also about knowing exactly what dependencies we use in our software and which version, how to find it. Like a lot of time when this vulnerability was first announced was spent by companies to figure out even if, like, are we even using Log4j? Not much on patching it, but like knowing if they were actually using Log4j, and that is a problem. The same year, we also got another incident with Travis CI. Back then, it was a popular build service used by tons of open source projects on GitHub for building applications. And Travis CI actually exposed secrets from these builds, secrets to access private container repositories or secrets to access cloud services. It was a disaster. So the services that we use as part of our production of software also impacts the overall security of our supply chain. Another example in the JavaScript world, there was this package, UA parser, that is used by tons of applications to gather data about the user agent, so about what browser users are actually adopting when using or navigating a front-end application. And that was a bit different from Log4j because it was an intentional malware, and the package got infected. Tons of applications started using the version with the malware. So how do we identify that before it hits production, before that vulnerability can actually be exploited? That's why we talk about supply chain security. And we need to identify all the different stages. I like how the technical advisory group at the Cloud Native Computing Foundation structured their paper on supply chain security. They identified 5 main stages we can secure. We start with our source code. We bring in dependencies, which typically are a big part of our software. Then we focus on the build, how we put together source code dependencies, how we ultimately package everything and deliver the artifacts to our customers, or even deploy them ourselves if we offer software as a service. Now, at each of these stages, there are security risks. There are certain impacts associated to each of these security risks. And today, I want to highlight some of them, going through all these stages. I'm Thomas Vitale. I work at Systematic. I'm a software engineer and architect there, really passionate about anything Java and cloud native. I combine these passions in order to write a book. It's called Cloud Native Spring in Action with Spring Boot and Kubernetes. And also, I'm a big supporter of open source technologies, contribute as much as I can, both in the Java space and in the cloud native ecosystem. All right, where to begin with supply chain security? Well, we'll begin from the top, source code. How can we secure our source code? Now, most projects are probably using Git. That's a great way to version control our source code. And Git, among other things, has a very critical feature that we really like when we want to secure our supply chain, which is the fact that it provides an audit trail of every change made to the source code. So if we identify a given change in the code, we can ask the question, who did this change? That's pretty useful, right? But then the next question is, once we get the answer from Git about who did this change, is, can we trust that answer? Can we really trust that information? Let's try it out. I have created a Git repository. It's basically empty. So I'll make some changes here. Let's say demo with Git. And since I'm just starting working on this repository, I want to configure my local Git repository so that I can commit with my personal information, with my personal account. So what I'm going to do is configuring the username for all my Git commits on this repository. And then I'm going to do the same for the email. So I'm using a special email address, an alias provided by GitHub, so I don't expose my personal email address. So now I can start making changes as myself on this repository. So I'll add the README file, and then I'll say commit changes to documentation, and then I'll push my changes. I mean, we do this all the time, right? Nothing special there. And then if I check the Git history for this repository, we can see that just now I committed changes to the documentation. And it was me, with a link to my account. Perfect. Now, you know, I often go to conferences with a friend of mine, Mauricio Salatino. He's not the DevOps this year, but maybe I can get his help contributing to this repository. Let's try that. So now I want to commit changes on Mauricio's behalf. So I'll configure his username, and I'll configure his GitHub account. On GitHub, he's called Salaboy. All right, let's make some changes. Supply chain security, I can add the README file, commit, updated README, and then I can push. So what is happening right now? Let's check the Git history. Who made this change? It was not me. It was my friend Mauricio. So let's, where are we? No, that's the wrong branch. Let's go back to the main branch, check the commits. GitHub even makes this into a link, so I can directly go into Mauricio's GitHub homepage. I can check out his book. By the way, if you work with Kubernetes, this is a great book. I recommend that. All good, but we all know that Mauricio didn't make those changes, right? I mean, you're the witnesses here. It wasn't him. That's the problem. So we want to use Git to keep track of every change applied to my repository, but I cannot really trust this information. So what can I do? Well, if I can't trust who did a certain change, maybe I can authenticate that person when committing the changes. So a solution to this is actually enforcing our Git repository to require signed commits. So each commit must be signed. I can sign it using a private key, like an SSH key or GPG, and only I will have access to my own private key, hopefully, so nobody else can commit on my behalf. A better way, I really like it, is a keyless approach. I don't know about you, but I don't like handling keys. They're really annoying. So a keyless approach is better because you don't need to create any keys in advance, but once you commit, then you're redirected to your usual single sign-on flow, maybe using login with GitHub, login with Microsoft, login with Google. It's an approach that I prefer. Unfortunately, using a tool like GitSign, there's not much support yet in Git platforms like GitHub and GitLab. I know they're working on it, but unfortunately, they still don't know how to validate keyless signing. So we have to fall back on keys. But the important part is that if a commit has a signature that cannot be verified, we want to reject that. And then every time we commit, we can add a little flag, -s, in order to sign that commit. And if it's not signed, our repository should reject the change. So I have already configured some keys for this Git repository. So if I make other changes here, once again, add the README file, add the commit message, I'm adding the -s flag. Now, important thing here, there are two flags in Git. One is uppercase S, and one is lowercase s. And I see this mistake done very often, even on articles about supply chain security and signing with Git. The little one doesn't sign your commit, even if it's short for sign off. That's used for something else. So make sure if you want to sign your commit, you use the uppercase S. And then I can say update README. I can push, and I can do that. I'm still acting on Mauricio's behalf, because Git doesn't have the concept of authentication. However, my repository on GitHub now can verify the signature. And you can see that now I have an unverified badge in there. So I committed a change with my private key, which is not Mauricio's key. So GitHub says, nope, that's unverified. That's not Mauricio's. Nice. Now if I change back to my account, so the username and the email, I'll make more changes. Add the README, add the commit, and I need to remember the signature flag, changes, and git push. And by the way, you can configure your Git client or IDE like Visual Studio Code or IntelliJ to always add the signature, so you don't have to remember to add the flag. But now if I refresh, we can see that it was me actually doing the changes, and I'm verified, so it was actually me. Now I can start trusting the Git history. And that's important because of a critical concept in supply chain security, which is called provenance. Let's move on. Provenance. Provenance is a proved and validated history of a component across its supply chain. So Git is an important part of it. We want to have a validated history of all the changes applied to our source code, and we want to validate that if a change has been done by me, then it was really me. So we need authentication for that. All right. Let's move on, because we start with source code, but typically we have multiple dependencies in our projects. I really like working with Java because unlike other ecosystems, we have a pretty solid and powerful set of tools that we can use, like Gradle and Maven. They're very convenient, powerful, robust, and we can manage dependencies in a convenient way. They're also quite straightforward to begin with, but now I would like to focus our attention on a few particular features. Now, you might think that some of these questions are perhaps silly, but not really. The first question is, where are we fetching our dependencies from? Now, it might seem simple, right? And simple demo applications like the ones I'm using, I'm fetching dependencies from Maven Central. But if you think about a real-world use case in the context of a company, maybe you don't have just one repository you're fetching dependencies from. Perhaps Maven Central is still there, but you might have an enterprise repository where your company publishes all the internal and private packages. So at that point, the question doesn't seem that trivial anymore. The next question is, which dependencies are we fetching? Again, might seem a silly question. If I add my application a dependency from Spring Boot, like the Spring Boot web starter, that's my dependency. But that dependency has transitive dependencies, and each of that transitive dependency has more transitive dependencies. So are we really in control of all the dependencies that we pull into our project? And if those transitive dependencies are the same library, but with different versions, how are dependency conflicts solved? Gradle and Maven, for each of these questions, have a different answer. They work with different strategies. So there's not even a single answer that I could provide right now. So when you go back to work on Monday, I invite you to think about these questions and try to see if you can answer in a complete way to all these questions for your projects at work. For example, just a little teaser let's move on. I have two projects. I have a Gradle project and a Maven project. In Gradle, I have configured the repository. I'm fetching dependencies from Maven Central, and I have two dependencies from Spring Boot. Maybe now I want to also fetch private dependencies from my company repository. So I can add a new Maven repository in here, URL, and my company repo /Maven, something like that. And then perhaps, since it's a very best practice when we talk about supply chain security, I want to remove Maven Central and have the central team in my company providing this repository also mirroring dependencies from Maven Central, so that we can centralize security controls. So every dependency pulled from the public internet then goes through our enterprise artifact repository. Now I want to try to do the same in Maven. So I have the POM XML, same dependencies. Let me zoom in a bit. And I want to add my enterprise repository. ID, enterprise, and some URL. company.com/Maven, yes, whatever. So now if I ask the question, where are we fetching these dependencies from? It's not that trivial anymore, because as you can see, there's no Maven Central repository listed here. Yet we are fetching dependencies from Maven Central. That's because Maven, by default, will inherit from what is called a super POM. So Maven Central is always enabled by default. So if from a security perspective you want to channel all dependency requests through your company repository, you have to remember to disable the Maven Central repository, which comes out of the box from Maven. So that's quite different from Gradle. And we have to say that all production releases for dependencies, they have to be disabled. So sometimes not trivial. But I want to talk a bit more about the middle question there. Which dependencies are we fetching? And also, if there's any conflict, what's the resulting set of dependencies that we're going to use? And I want to talk about SBOM. This is a software bill of materials. And you can think of it as a list of ingredients that make up software components. So if I go to the supermarket, I buy a box of cookies. On the box, I can see the list of all the ingredients. In the same way, I want to attach this inventory, this list of ingredients, for all the software artifacts that I produce. So I always know what's inside my software. So if someone asks, are you using log4j and with a vulnerable version, then I can immediately answer. Now, SBOMs in general are just a way to deliver that information, but we probably want to standardize the way we exchange the information so that it's both useful to humans, something readable, but also useful for machines to read and do some automation and computation on it. There are different formats in the industry. The two main ones are CycloneDX and SPDX. Now, it's not really important which format you use. You can always convert from one format to the other. The important thing is actually generating an SBOM. In the example, I'm going to use the CycloneDX format, but again, not important. The important thing is actually generating an SBOM. And now the next question is, why do we need one? We don't need one because that's the best practice in terms of supply chain security. It has to make sense. So I always like to ask, why? So why do we want an SBOM? Well, we want to get this inventory for all the software components, so we always know what we are putting inside our software package. But then once I have that list, I can enable new use cases. I can go through all the list of dependencies and check if there is any software vulnerability. If I don't know what dependencies are in my software, I cannot really search for known vulnerabilities. Same thing for licenses. Many companies have different policies in terms of licenses. Maybe an open source license is fine, but maybe we want to check if we are actually using or misusing a dependency against the license. If it's something more restrictive or something more enterprise, we probably want to know that before we get to production, before we get in trouble for breaking the license. And then we can also find outdated components. Because if we know that we're using a certain vulnerable version of log4j, then we can also check, is there any new version that I can use, perhaps that has the security patch? And we can also verify the integrity of each of these components. So am I really sure that I'm downloading that specific dependency from its provider? Or was it tampered with? We can use SBOM to do that. All right. We know why do we need SBOMs now, but when should we generate this list of ingredients? There's usually some debate around this, because, for example, a common way, I call it the lazy approach, is at the end of your pipeline, once you have your artifact, jar file, container image, you use a tool like Snyk and say, please generate an SBOM. And those tools will try to break the package apart and figure out what's in your package, what's in your software. But that would be like having the cookies, the box of cookies, after they have been wrapped and boxed, and then you ask, which ingredients did I use to make those cookies? And then you open the box and try to infer with any kind of chemical process and figure it out what's in those cookies. Maybe not the most efficient way. So perhaps we can do it on the source code. I mean, that's the source code. We know we can trust the source code. We can generate one from that directly. And that works. It's actually more accurate, but it probably includes additional things that we don't want as part of the list of ingredients. Because if I'm preparing to bake some cookies, maybe I have all the ingredients on a table, I have all the different tools, and maybe the spoon that I use to taste the dough, I don't want that as the list of ingredients. Similarly, in an application, I might have different dependencies I use for testing that are quite useful to be monitored as part of the source code stage of the supply chain, but they don't end up in the final artifact. So maybe we're talking about two different bill of materials, one that is for all the sources and one that we associate to the final artifact. Now, the approach that I prefer is actually making the SBOM generation part of the build lifecycle. And the reason why is that the build lifecycle, if we take Gradle or Maven, they know what dependencies they are putting inside the final artifact. So why not taking advantage of that, so that we get the most accurate bill of material we could get? And the CycloneDX project actually is publishing two plugins, one for Gradle, one for Maven. So if I say Gradle build, then I get automatically a bill of material. And as a developer, I also like this approach because I don't have to do much. I just need to make sure to include the plugin. And the same thing is for Maven. I'll share the slides afterward with all the source code and instructions, so you can try that later if you like. But for now, I want to show you a quick demo. I have my Gradle project. So if I run a build, not only I will obtain a jar file, but I will also obtain a bill of materials. So let me zoom in on one of the components so we can see an example. Let's see, we have Apache Tomcat in here. We can see the version, the name of the dependency. We get all the hashes, so we can actually check the dependency for integrity. Maybe it's been tampered with, but with the digest here, we can actually perform that validation. We have the information about the license. It's Apache 2, open source, great, I love it. And we get also a unique URL that identifies this package. This is the information that vulnerability scanners use to find out if there's any vulnerability associated to this specific package. Great. We got an SBOM. Now what? Well, first thing I might want to do is extend my pipeline so that after the build phase, I take the SBOM and I use a vulnerability scanner like Trivi and scan the full list of dependencies in order to find if there's any known vulnerabilities associated to any of that dependency. That's probably the first thing I want to do if I have an SBOM. But we saw we have different use cases. So perhaps it's worth investigating not just tooling, but also the practices that we have in order to manage and actually use this SBOM. I want to show you an example of how to manage these supply chain security risks with a tool. It's called Dependency Truck. It's an OWASP flagship project. I really like it. It's fully open source and free, and also it's written in Java. So you can run it as a Java application, you can run it as a container on Docker, on Kubernetes. And it really empowers us to get the most out of SBOMs. It provides a REST API, so as part of your pipeline, once you generate the SBOM, then you can send an HTTP post request to the API, and from there, I'll show you what different things we can do. So this is how it looks like. I have already some projects with some vulnerabilities that I want to keep track of. If we check our demo application, we can see a few different things. First, all the components in my application with the version, the group, the license, and even a flag if there is a newer version. So I might want to consider updating that. And then there are some vulnerabilities. So this is a Spring Boot 3 application. I can see that there's a vulnerability, critical vulnerability with Snake YAML. This is the library that Spring Boot uses to deserialize my configuration from a YAML file. So it seems like I can't really put this application in production, right? Now, this is the tricky part. We get a list of known vulnerabilities for our SBOM, but are we really vulnerable to that? And there's no fully automated way to infer that. So right now, as humans, we actually have to investigate and go through all the known vulnerabilities returned from the vulnerability scanner and verify, is this actually affecting my application or not? Well, in the case of Snake YAML, I actually know that Spring Boot is not vulnerable to this, because this is about unsafe deserialization. Well, Spring Boot is doing a safe deserialization, so Spring Boot is not impacted. And my application is not using this dependency directly, so overall, my demo application is not impacted, but what can I do? Any vulnerability scanner would flag this. Maybe I get a call from a security team in my company or from the customer yelling at me, hey, you deliver something with a critical vulnerability. What do we do? We have actually recently been introduced to a new standard which complements SBOM. It's called VEX. What I can do from this tool, but it works in general because it's a standard again, I can perform an analysis. I can say, this is a false positive, or actually even better than that, I'm not affected because the vulnerability is in the library, but my application is not affected. And then I can write why. Well, it's protected by mitigating control. I'm not using the vulnerable part. I can say that my response as a vendor is that I will not fix this dependency because I'm not impacted. So now I need to deliver this information in a standard way so that I don't get called by 100 different customers asking information about why didn't I fix this vulnerability, or from my colleagues or from the security team in my company. And that's where VEX comes handy. So I can export the VEX document from here, and I can attach it together with my application artifact and my SBOM. So it's not enough to scan for vulnerabilities, but we also need to deliver information about what are we doing with those known vulnerabilities. Another outcome could be, hey, I'm looking into this, we are impacted, I'm analyzing the situation. And then I would say, well, it's exploitable, so I'm maybe gonna update, or I'm gonna roll back. So it's a way to communicate to the consumers of my software what am I doing with some vulnerabilities. That's called VEX. It's still kind of new, so there's not extensive support in the ecosystem, but it's evolving quite quickly. And I think it's really needed. It's a vulnerability exploitability exchange, a vulnerability document designed to complement an SBOM, because we need a way to inform users of a software product about the applicability of one or more vulnerability findings. Great. We talked a lot about dependencies. We mentioned a few things about builds, but maybe we can spend a few more words on it. Again, in the Java ecosystem, we have a quite convenient and powerful way to build our software. Again, Gradle and Maven are a great help there. And if we take, for example, Spring Boot as an example, but this applies to any Java application, we now have three main ways of packaging our application. I can build a jar file, and from Gradle and Maven, I can do that. And I know that with the right plugin, I can also obtain a bill of material. I can package it as a native executable using graalvm. And here it's even more important that we generate the bill of materials as part of the build process, because at the end, we won't get enough information for vulnerability scanners to actually find which components were part of it. And that's one of the beauty of native executables, that you only get the code that you execute. That reduces the surface attack, so it's good for security, but it's also important to generate the bill of materials at the right time. And the right time is during the build. And finally, we can build a container image. Now, how many of you are packaging your applications as container images? I'm curious. And how many are using Docker files? Now, Docker files are a quite simple approach. I always say that writing a Docker file is easy, but writing a Docker file, which is production grade, that's a bit more challenging. And I like to quote Josh Long here, saying that friends don't let friends write Docker files. As a developer, I don't like writing Docker files. I know how to write them. I investigated all the different best practices to do it in a secure and performant way, but I really want to focus on my application code. Because if I write the Docker file, then I'm responsible for it. I have to maintain it, I have to update it. And at the end of the day, maybe it's not even that secure as I thought, considering all the time spent on it. Quoting again from the supply chain security paper from the Cloud Native Computing Foundation, they write that Docker files are easy to write, but the current development guidelines do not produce containers that are repeatable and hardened. So, is there any way we can improve this? I really like working with a project called Cloud Native Build Packs, which converts your source code into container images. It doesn't require any Docker file, and the beauty of it is that it's a polyglot tool, so it works across different languages and frameworks. So you can use it with Spring Boot, you can use it with Quarkus, you can use it with Open Liberty, or you can use it with Golang or .NET application. You run one command, for example, using the pack CLI that comes from the project, and you obtain an image. And if you're using Spring Boot, it's even easier because it's embedded in the Gradle and Maven plugins for Spring Boot, so you don't have to install additional CLIs. So besides not having to write a Docker file and obtaining a production-grade container image, one of the important features of Cloud Native Build Packs is reproducibility. So let me explain. We want to eliminate any source of non-determinism. So over time, let's say last week, I had my application, I built a container image out of it. If I try again today to build the same application, unchanged, same source code, will I obtain the same container image? If the input is the same, I want the output to be the same over time. And that's usually not true when working with Docker files. But with build packs, we can achieve this reproducibility of the build. Same input, I want to obtain the same output. Otherwise, there's some non-determinism in the build that will affect my supply chain security posture. I'll show you a little demo now. I have a Gradle application. Same thing will work with Maven. So I can say boot build image. This will build my image in a performant and secure way. I can also use different tools. If you're working on Kubernetes, there's a Kubernetes implementation of build packs. It's called kpack. So you can actually trigger the build via a specific resource called image. You point to your Git repository, like I'm doing down here, and every time there's a change in the Git repository, I can obtain a new container image pushed to my container registry. And then some configuration for the build. Of course, I'm using Java 21, the latest and greatest. Okay, I obtained the image. So now I can take the name. It's built locally. I'm using Podman. I really like it to manage containers. It's open source and free project. Let's check the image, search for demo. And now if you look closely, it says that this one has been built 44 years ago. There must be a mistake, right? Like so many people, the first time trying Cloud Native Build Packs, then they see this and, oh my gosh, what happened? Like, I wasn't even born then. Like, how is that possible? Is that magic? Have I been hacked? No. That's an important feature, actually, to have there, because the creation time will always be the same, January the 1st, 1980. And that's because we want reproducibility. If we use the real creation timestamp, then every time I build the image, it will be different because the timestamp will be different. And now I can hear you asking, yeah, but what if I want to know when the image was built, the real time? Well, hopefully you have that information in other ways, because if that's the only way you can tell when the image has been built, I think there are other issues in your supply chains to solve first, because we need to ensure provenance and auditing of the entire build process. So that information can be retrieved elsewhere, and we'll actually see that in a second. So it's not a big deal not having the creation timestamp here. By the way, you can make it non-reproducible. There's a flag, both in Spring Boot and build packs, if you really want the creation timestamp, but then you lose the non-determinism, or you introduce non-determinism. But that's up to you. All right, moving on. I built my image. Let's talk about artifacts. So far, I have 2 artifacts, maybe. I have my application artifact. That could be a container image, jar file, native executable built with GraalVM. And I have an SBOM. What do I do now? I want to make sure that I sign those artifacts. This is the same problem we have with Git. We want to know who actually built those artifacts. We want to know if I'm using a certain service from a vendor. I want to be sure that I'm using the same version built by the vendor. So I need signatures. In a similar way, we handled Git. So I can sign my binaries, like a jar file, native executable. I can sign container images. And I can even sign the SBOM. And I can use a tool like Sigstore Cosign, which is quite popular also in the cloud-native ecosystem. It's integrated with a lot of different tools. And it's quite easy to use. So I have my image. Now I'll tag it so that it points to my GitHub Container Registry account. And then I can say cosign, sign, and then I'll sign the image. Like that. There it is. That's the keyless approach I mentioned earlier that we can also use with Git. I don't have to configure any keys. I can say login with GitHub, and I'm done. Finally, I really don't like managing keys. So how many of you like managing keys? One person. Cool. Respect. Yes. All right. I mean, it's easy, right? We have a signature. But, we have a problem here. I mean, I just built a container image out of a random Git repository on my machine. I sign it. So you know that that image is signed by me. But you don't know where it comes from. You don't know what code I put in that, right? We don't have that traceability, the provenance back to the source code. It could be anything, even if I just built image in front of you, but you don't know exactly what I put in that project, right? So signatures are not really enough. So that's the problem that the Salsa framework is trying to solve. Salsa stands for Supply Chain Levels for Software Artifacts. And it's all about ensuring integrity for the software artifacts across a supply chain. And the first area that they analyzed and tried to come up with guidelines to protect is the build. And it's all turning around this concept of provenance once again. So if I build a container image, I want to know where it comes from. I want to know which commit hash from which Git repository it's coming from. So I want to know exactly all the steps through which my artifact was produced. And that's the same that we have in the supermarket. If I go to the supermarket, I buy some oranges, then I can check the labels. I can see it's validated by the European Union, and the oranges come from Italy in Sicily. And I can even see the farm where the oranges came from originally. I want the same thing for software. So Salsa provides 3 levels, 3 supply chain security levels. So we can start with level 1 and then move our way to the top. The first level is we document where our software comes from. But there's no guarantee that the information is accurate or even valid. It's just documentation. Second level, we want to run the build on a hosted platform that generates and signs the provenance itself. So we also want to sign the provenance. It needs to be authenticated. And the third level is doing the same, but the provenance needs to be non-falsifiable. Now you're probably asking, okay, again, I'm a developer, I want to focus on my application. Why do I need to study all of this? Well, actually, as a developer, I don't need to know all these details, because this is something that the build service has to provide, actually. So I'm using GitHub, and the Salsa project itself has provided an implementation for GitHub to generate and sign the provenance. I don't have to do anything myself. I just need to call into that function as part of my pipeline. So now I want to show you something similar would work, for example, on GitLab. The syntax is different, but the concept is the same. I have a pipeline that I run on my GitHub project using GitHub Actions. You can see all the steps. I check out the source code. I configure Java. I compile my application, which also generates the bill of materials, of course. I upload the bill of materials. So, for example, I can push it to dependency track, the service we saw earlier. I also use Trivy in order to scan for vulnerabilities and block everything if there's any critical vulnerabilities. And then from the other solution, I can actually audit all those vulnerabilities. And we build the container image. We also scan the container image. So we have this scanning both on the original source code, but also on the final artifact for enhanced security. We publish the image. Then down here, we sign the image. And this image is signed using that keyless flow. So we don't have to worry about maybe exposing the private key, like it happened to Outlook some time ago, for example, or it happened to other projects that they leak the private key, and then suddenly they have to rotate all the keys, and you need to be aware of that. With the keyless approach, you don't have that risk. And finally, that's the interesting part. I call the Salsa provenance generator for GitHub from the Salsa project. I only need to make sure that I'm calling that functionality and that I'm providing the information on my application artifact. And that under the hood, they will create the provenance, tracking all the steps in my supply chain, so I can see the source code, the specific commit, the dependencies, and it's signed. All right, we are getting to the final step now, because we are producing all this metadata, all these different steps in order to ensure provenance and integrity of our software artifacts and supply chain. But when we get to the deployment, we actually have to use that information. Otherwise, it's useless. It's not something that you check a list like, oh, are you signing your artifacts? Check. You also need to use that signature for something. Otherwise, it's pointless. Always ask, why are we doing this? So we want to validate all those artifacts metadata in order to ensure secure deployments. And if you're operating the software yourself, that's something that you will do in your company. But if your clients are actually deploying the service themselves, then they can also go through all these steps and be sure that the software that we as vendors provide them is actually secure, we ensure integrity, and it's all valid. So I can verify the signatures, I can verify the Salsa provenance, and I can verify the vulnerability report. So I need to provide also this information about bill of materials and the analysis on the vulnerabilities found using the VEX format. So once again, we go back here. I can use the cosine CLI in order to verify. Let me zoom in a bit. So the cosine CLI has a way to verify the signature on my application. Of course, I need to provide the identity that I think signed this image, right? So I'm providing my own identity from GitHub. And then if I run this, I can verify if the signature is actually correct. So you're going to get a huge JSON file, but what is important is this. The cosine claims were validated. The signature is valid. Cool. It was really me building this image from GitHub, so in a controlled and secure environment. Great. What about the provenance? I can use a tool from the Salsa project. It's called Salsa Verifier. So I can run this. I will also print the provenance so I can show you what it contains. Scrolling up, so we can see passed, verified Salsa provenance. Great, and we find information about the specific container image, the digest. Never trust version numbers. You want to verify on digest. That's the only secure way, because tags with a version number can actually be applied to different commits or different digests, so we cannot trust it from a security perspective. And we have information about the Git repository, so you can see it comes from my supply chain security Java repo that I'll share with you at this specific commit. And I'm running things from this workflow. So I also get information about all the steps used during the build phase as part of the pipeline. Now, you can do it through the CLI. There are different tools at integration based on your pipeline engine. If you're on Kubernetes, you can even use a policy engine there. For example, Caverno. You can define policies in Kubernetes to ensure that every application coming from my container registry, in this case, is correctly signed. So you can define the criteria here. And if it's not, if the signature verification fails, then the deployment fails automatically. So you always ensure that you get the right state and the right secure state in your production environment. And same thing with the provenance. I can create another policy to verify the image provenance. Again, I apply this policy to images from my container registry on GitHub. I want to verify that there's a correctly formatted provenance for Salsa. And by the way, we are achieving Salsa level 3 with GitHub, so it's the highest level, which is really great to have out of the box. And similar way on GitLab. And then we want to verify on the condition that the provenance is actually being generated by the official generator from the Salsa framework project that you can see here. All right. So we went through different stages now. We went through the source code, dependencies, build, artifacts, and deployments. I'm going to share some resources with you, the source code, the slides, and some extra details. But I really invite you to think about all these stages, because it's not about following some guidelines, but it's more about managing security risks. Security is all about managing risks. So what makes sense in a specific context might not make sense in another context. So always validate all these ideas and all these patterns, just like in the case for the SBOM. So if I want to create one, if it makes sense to create one, identify the use cases and figure out if it makes sense in your own context, in your own company. By the way, in the US now there's a regulation that in order to provide software to public entities, you have to provide an SBOM, and it has to contain specific information. And in the European Union, I think next year also a similar regulation will also start being applied, that SBOMs will be required, and information inside the SBOMs also will have to be in a certain way. That's why it's important to consider when we create one, because if it's missing important information, even if you get an SBOM, if it's not compliant with the regulation in your own country, then it doesn't make much sense. Thank you very much for joining this presentation. I'll be around for some questions. I think we have 2 minutes. Otherwise, you can find me in the hallway, and have a great rest of the day. Any question? Yes?
One question. In the beginning, you showed me that it's important to check where the dependencies are coming from, and you are using the patches to check the dependency of change. I know that's how it is. For some change design, we want to be sure that all the dependencies are really from the vendors and not manipulated by somebody else.
If I understood the question correctly, it's about how do we verify the integrity of certain dependencies, like when we get the Spring Boot dependency in our project. Can we use some hashes to verify that? Is that the correct answer? The correct question?
But I need to, I can only trust signatures. So, is there something available to check if
Yes. So, unfortunately, like a lot of dependencies are still not providing the signatures attached to them. But for example, when using Gradle, there are built-in functionality that you can use. I can show you. There is a functionality to generate, to resolve the hashes, so that every time you build your application, if a hash changed, the build fails. And there's a functionality to verify the signatures if those dependencies come with signatures. You can find an example with instruction in the source code on GitHub. It will be in the dependency management folder. Let's see a quickly show an example down here. So there is a task that you can use to create that verification metadata that will end up in your Git repo. And if hashes change, this will fail. And similarly, you can obtain the signature and validate those. This will end up in an XML file. You can see a snippet here where you can decide whether you want to verify just the metadata, like the hash, or also the signature. And another interesting thing in Gradle is that out of the box, you can get a log file where all the dependencies are locked on specific version. And you can put a file like this in your Git repo where everything is resolved with the right version and where is it used? Is it used at runtime? Is it used for testing? So you can be more in control when you change some dependencies if something else you were not expecting to change also changed. And this will be part of the build lifecycle. So if something changed without you knowing, then it will fail the build, which is, I think, really great. This is out of the box in Gradle, starting from version 7. For Maven, there is a plugin that can be used to this purpose, and it's also documented in the repo. So if you're using Maven, you can achieve the same thing, and it's documented here. So time's up, but I'll be around, so if you have more questions, feel free to catch me afterwards. Thank you, have a great day.